So in the previous lecture, we were discussing binary trees, and we were looking all the features that are available regarding your binary trees. That means we're adding a node to your tree. We're trying to find a particular piece of information, a particular piece of data from your tree. And we saw how a tree stores its information, how data is organized within a tree. So starting from the very root to all of these leaf nodes, either moving to the left or the right, what principles are involved in deciding between moving towards left and right. We discussed this in great detail yesterday. Now, one of the features of binary tree is in order tree traversal. Now, in order tree traversal means that I access all of the nodes in the tree, and I turn by turn return all the values that are stored inside the node to make sure that the values are presented in order. And the thing is, for in order, I have to present all of my values for in order tree traversal. I have to apply the technique of recursion. After applying recursion, we can use that method to access all the nodes in the binary tree. Now, first of all, let's try to understand what recursion is, what a recursive function is, so on and so forth. First of all, what is recursion? In mathematics and computer sciences, a recursive routine is one that is defined in terms of itself, plain and simple. So in simple terms, if we are talking about a recursive algorithm or recursive function is a function that has basically, it's a function that's calling itself in its definition. So as you can see here, this function is called factorial. So what factorial does, we'll look into it in a minute, but as you can see here, the function definition stated right here actually is calling the function that we're defining as well. So the function factorial is defined by calling itself. So this is a recursive function. This is a recursive subroutine or recursive call, in which when I'm defining a subroutine, there is a call to that subroutine within the definition of the subroutine. A recursive function, that's what it is. So let's look for recursion. We will actually look at the process of getting a factorial, because finding a factorial is in a way a recursive process. And we can use this example of finding a factorial to implement it to find a recursive algorithm. We can define it in a recursive manner. Okay, first of all, let's define what a factorial is. So basically, factorial is a mathematical operation. So if I want to, for example, find the factorial of 4, we define it in this way: 4 by this followed by this exclamation mark. So basically what this means is that I'm trying to find the factorial of 4. And what is factorial of 4? 4 factorial is basically 4 multiplied by 3, multiplied by 2, and multiplied by 1. So the result that I get here will be considered as 4 factorial. So in a way, 4 factorial can be said to be as 4 multiplied by 3 factorial. So basically what I'm doing is I'm multiplying 4 with the factorial of 3. And what is the factorial of 3? 3 multiplied by 2 multiplied by 1. So in a way, we can say that if I were to define an equation for factorial, it can be very easily defined in this manner: that if I want to find the factorial of n, what I will do is I will basically multiply n into the factorial of n minus 1. So to find 4 factorial, I can simply multiply 4 with the factorial of 3, and I'll have 4 factorial. Simple as that. So the formula n, if I want to find the factorial of n, it will be n into the factorial of n minus 1. So that's how we can use this formula to basically find a factorial. However, there is one confirmed case that if we want to find the factorial of 0, the procedure of finding a factorial states that all values are not yet known, but it is confirmed that 0 factorial will always be 1. So that is one value that I know instantly. 4 factorial, I'll have to multiply and find out, but 0 factorial is confirmed. 0 factorial will always be 1. So that's what we know about this. Okay. For a recursive function, I have basically two cases. A recursive call or a recursive function is made up of two cases. There's the base case and a general case. So basically what happens is that the base case is basically it's a recursive call that eventually results into an actual answer. So basically, if I were to say that what do I know? I know the confirmed value that I know is 0 factorial. So that is my base case. However, that's the value I know, but I don't know yet the value of 4 factorial. I don't know the value of 3 factorial. I don't know the value of 2 factorial. I don't even know the value of 1 factor. But what I do know for sure is 0 factorial. So what I do is that I make a recursive function in such a way that in each recursive call, I am using my general case in which I will be in each general case, I will be eventually moving towards my base case. So in this case, if I were to say, I want to find the value of 4 factorial, for 4 factorial, I need to first find out the value of 3 factorial. Okay, let's find the value of 3 factorial then. Okay, for the value of 3 factorial, I must have to find the value of 2 factorial first. For similarly, if I want to find the value of 2 factorial, I must find the value of 1 factorial first. And for 1 factorial, I will have to find out the value of 0 factorial, which is the value that I know for sure. So using the value of 0 factorial, I will implement it and find the value of 1 factorial. Once I have 1 factorial, I can use it to find 2 factorial. And once I have 2 factorial, I can use the value to find 3 factorial. And when I have 3 factorial, I will find my eventual result, which is 4 factorial. Okay. So having said this, my general case, there are multiple general case calls. In each case, I'm going from 4 to 3, then 2, then 1. And as you can see here, in each recursive call, I'm going one step closer to my base case, which is 0 factorial. In any recursive function, my base case is the case for which the value is known. In which case, factorial is 0 factorial. I know the value of 0 factorial is 1. So that will always remain my base case. But in each iteration, n factorial, n minus 1 factorial, whatever it is, every recursive call will eventually make me closer to my base case. And when I reach my initial base case, that is the first instance where I will actually know the value. And I will use that value in the upper layers, eventually get the final result. So the base case involves getting a solution without involving the general case. So this is just the value that I know for sure. So in this case, 0 factorial, no, I don't have to worry about finding any other thing. I just know for sure 0 factorial is 1. The general case is defined in terms of the definition itself. So basically, it's a recursive call. So each time for a general case, I will have to find a lower general case and lower general case. And eventually, I will reach the base case. It is important that the general case comes close to the base case after each recursive call from each recursion from the starting point. So unless that's happening, if that doesn't happen and at each recursion you're not actually moving close to your base case, you will never end this recursive function. So it's very important that at each recursive call you are a step closer to your base case. Like we said, first for 4 factorial, we will move towards 3 factorial, then we'll move towards 2 factorial, then 1 factorial, and 0 factorial. 0 factorial, I reach my base case, and that's the actual value I know. So in this case, as you can see here, 0 factorial will be my base case, and the function that n into n minus 1 factorial will be my general case. At each step, I am first of all finding the general case, and I won't have the value, I won't have the results right away. But at each recursive call, I will start moving towards my base case until I eventually reach my base case. And that's the first time I actually have a result. And using that result, I will move to the upper layers in return and finally find the whole factorial function that I want to find. So in this case, if I have 4 factorial, I will first have to find 3 factorial. If 3 factorial I want to find 3 factorial, I will have to first find 2 factorial. You see how I don't have any answers yet. I don't have any answers yet. I'm still investigating it. And at each iteration, I'm moving close to my base case. For 2 factorial, I will first find 1 factorial. And for 1 factorial, I will first find 0 factorial. And this is where I actually have a value. I've actually have an answer which is explicitly defined, which is 1. Now, since I have an actual value for this and I have found 1 factorial, I can use the result of 1 factorial here and find 2 factorial. Now, since I found 2 factorial, I can use the result of 2 factorial and find 3 factorial. And if I found 3 factorial, I can finally find my original value that I was looking for, which is 4 factorial. So basically, I go down in layers to my base case. I get my first instance of an actual explicit result, and I use that result back, carried forward back in the upper layers till I reach my original value. As you can see in this trace table right here, this trace table highlights the sequence of events that take place to eventually finding my final value. So for example, I'm trying to find factorial of 4. So basically I do a procedure call. My procedure's name is factorial and I'm passing a parameter of 4. Okay, in this algorithm, in this procedure, first of all, as you can see here, this is the algorithm for factorial. Now, as you can see here, when I pass a value as a parameter to my factorial function, let's say that is n, when the code, the sequence enters the procedure, it will first ask this question: is n that I just passed as a parameter equal to 0? That what that means is that have I reached the base case yet? If I have, then I will simply return the value result as 1. However, if I haven't, in this case, this condition will become false and I will go towards the else state. In the else state, let's say I passed 4 for this, n is 4. So n is not equal to 0 because n is equal to 4, in which case this condition will become false and I will come in the else state. Over here, what I will do is, first of all, okay, you want n factorial, no, sorry, you want 4 factorial. First, you will have to find the n minus 1 or 3 factorial. So as you can see here, now I have started a new line of execution of a function call, this time with n minus 1, in which case that's 3. So I have passed 3 for this function, and you can enter another layer. Now imagine that I have now started factorial function execution with the parameter 3 all over again. So it's now I'm comparing 3 with 0. Is it base case? No, it's not. I'll move to the else state, and now I will start a new layer, this time with 2 as a parameter. And this introduces a next layer of introduction that's with 2. Is 2 equal to 0? No, it isn't. I'll come in the else state, this time with 1. As you can see here, eventually when I get the factorial of 0, parameter is passed as 0. This condition becomes true then. And that's the first instant of an actual explicit value I have. And I will use this value and pass it to the upper layers, find another value, pass it to the upper layers, till I eventually reach the 4th input, where n was equal to 4, and I have the final result available. This diagram makes a little more sense here. As you can see here, I started off with factorial 4. So for factorial 4, first I will have to find factorial 3. So that's why what the formula was n into n minus 1 factorial. So that's what's happening here. For 4 factorial, I will say, because it's not equal to the base case, I will move towards this execution. 4 into factorial 3. So 4 into factorial 3. Now, for factorial 3, I started a new layer of execution, a procedure call with 3 as my parameter. So in this case, n into n minus 1 factorial will be executing for this new line of execution of subroutine. It's a sub layer generated from this original first procedure call. So in this case, for factorial 3 to be done, I have to first calculate factorial 2. For factorial 2 to be done, I will have to first calculate factorial 1. And for factorial 1 to be done, I have to first calculate factorial 0. And I know the result of factorial 0. Now imagine this. I have the value of factorial 0. My result is now 1. And I will return this value 1. So for factorial 1, I returned the value 1. So I will go back in the upper layer with factorial as a parameter 1. This returns the value 1. 1 multiplied by 1. I now have the value for factorial 1. I return the value 1 right here. This factorial 1 function call results in the returning of number 1. 1 multiplied by 2 will become the value of result over here. And I will return the result in this function. So I will return 2 from this procedure call. So that means when I go back in the upper layer, factorial of 2 will result the answer 2. I will use that 2 here, multiply by 3 here, and that value will be saved in result. And I will return the value of 6 here. So 2 multiplied by 3, the value of 6 will be returned. And that means the function call for with parameter 3 will return the value 6. So that means in the upper layer, when this procedure completed, it returned the value of 6. 6 multiplied by 4 becomes 24. And that's where I will actually have my value, my final result, which I was looking for, will return 24. So basically, if you come back and look at this, this is what we're doing. We're going into layers, layer-wise. We're trying to investigate where I have an actual value, an actual final defined result. And that will obviously be my base case. So as you can see here, my general case, with general case is n into factorial of n minus 1. At each layer, my general case comes closer to my base case, which is factorial of 0. And if this is not the case, if I'm not moving one step closer to my base case, my recursive call will not end and it will never reach the final result that I'm looking for. So it is very important for a recursive call to end at some point that I move closer to my base case after each recursive call. Now, if we come back to the table over here, so as you can see here, my table has these columns. Call number refers to what instance of this procedure call is it. So this is the first time factorial function has been factorial subroutine has been called, and this is the parameter used. Okay, what parameter are being used for? I'm using 4 in this. And what does this mean? It means that have I reached my base case? Base case is, as you remember, n equal to 0. N is equal to 0 is my base case, n is equal to 0. So have I reached n is equal to 0 yet? No, because my n is equal to 4. So that's why it says false here. What is the outcome of this first procedure call? The outcome of first procedure call is now I'm going to a further deeper investigation. Now I will find 4 into the factorial of 3. Okay, what is the factorial of 3? This will result in my second procedure call with a parameter of 3. Have you reached the base case? No, we have not. What is the outcome of this procedure call? It is 3 into factorial 2. So that will be my third procedure call with a parameter of 2. Calling the third factorial function third time with a parameter 2. Have we reached base case? No, we have not. So what is the outcome of this procedure call? 2 into factorial 1. 2 into factorial 1. Have we reached base case? No, we have not. So this will result in my fourth procedure call with the parameter of factorial 1. So no base case yet either. The outcome of this procedure call will be 1 into factorial 0. And that means I will now start finding out the factorial 0. This will result in the fifth time I'm calling the factorial function. So this is my fifth layer of factorial calls. This, however, will yield as true when I'm comparing the base case, because base case is n equal to 0? Yes, it is. And the outcome of this procedure call, since the base case is achieved, the outcome of this procedure call will be 1. Now you can see here, after the first time I've reached the base case value, I will start returning numbers. This factorial 0 will be returned multiplied with 1, resulting in the result of factorial 1. As you can see here, I use this one to multiply by 1 to find factorial 1. Outcome of that is 1. After that, I have factorial 1. I will take the value of factorial 1, multiply by 2, get the value of factorial 2, which is 2. Now I have the value of factorial 2, which is 2. I will take that and multiply by 3 to find the answer of factorial 3. And finally, when I have the answer of factorial 3, I will multiply it by 4 to finally find the answer of factorial 4. And basically, you're unwrapping. Your result starts to unwrap once you have reached a base case. By comparison, if you want to achieve the same result using not a recursive call, but same result using, say, a loop, this is what it would look like. So I've got my function here, factorial, we pass a parameter as before, and it will return an integer value as always. I have a result is equal to 1. I will start off with this. I will have a loop that will run from, this is my counter variable, I to n. N is the parameter I've passed. So basically, if I've passed 4, this loop will run 4 times. And at each iteration, and what I'm doing is that I'm multiplying 1 into the counter value. So 1 into 1 for the first time, saving it at result, then counter increments. Result is now 1 multiplied by 2, saving a result. Next time it runs, the result is now 2. 2 multiplied by 3, 6. 6 multiplied by 4, 24, and that's where my loop enters. So we can do the same thing with loops, but a recursive call is much more efficient in terms of execution as opposed to a simple loop. So this is an alternate. We can use it this way, and however, if you want to use factorial function, we can do it this way as well. Some applications, it's not necessarily because of the execution time. Sometimes some applications strictly require a recursive call. So the original application that we're studying this for is for binary tree, and binary tree handles its in order tree traversal using a recursion. This is what, that's why a recursive call is being used. So it's not always the cost that is involved, is sometimes that only recursive procedures can be used. Now, let's look at this example. As you can see here, the algorithm states that there's an unnamed algorithm. So it's just calling it X. So why it's called X is because we want to, it's asking the purpose of X. So once we make a trace table, then we'll find out what it does. So basically what's happening here is that procedure X takes a parameter N. The condition is tested is N equal to 0 or N is equal to 1. If either one of the state is true, then I will simply output the value of N at that time. However, if this case is not true, then I'll go into another recursive call. So in simple terms, if I were to distinguish between the base case and general case in these two, this was my base case because it's yielding an actual value. And this is my general case because it has another recursive call. So to simplify the whole process, we can say that the base case outputs an actual value, a known value, whereas the general case will have the recursive call in it. So even in this example, you can see the recursive call is taking place in the else condition. So this is my general case. Same thing goes over here. If you look at my factorial function, my recursive call takes place in the else state. So this situation is my general case. So wherever the recursive call is taking place, that is known as a general case. And where an actual output value is being, an actual value is being output or returned, that would be my base case. And you will be asked this in your exam at some point. You will, maybe there have been questions in the past where an algorithm is written in front of you and you're supposed to identify the line that states the base case and the general case. So a rule of thumb states that if it is outputting an actual solid value, it's the base case. And if it is resulting in another recursive call, then it is my general case. Anyway, so what's happening here is that, let's look at the trace table. So I'm starting off with the value 19. So we're going to be running this algorithm with the value of 19. So my first recursive call will be with X at parameter 19. My condition is asked, is N equal to 0 or N is equal to 1? In other words, has my base case been achieved? No, it has not. So what it will do is that I will have what's the outcome of this first procedure call is that I will move on to the general case, and in which case I will be moving towards another recursive call, this time with the value of 9. Now, why 9? Because I'm passing the value n, which is 19, div2. Now, if you remember, div2 means that my answer is written in this way, that I have 19, and I simply consider div2, I just simply consider this quotient part. It doesn't matter what I have achieved as a remainder or year, whatever. I'm not worried about that. I just want this answer. This is my result of this operation. So in this case, the second recursive call will result in x being passed the parameter value with 9. And at the same time, there is always also being an output carried out at the recursive call. So then what we'll do is we'll output the value of n mod 2. So at that time, I have n as 19. Mod is what? Mod returns the remainder. So if you look at this division statement right here, simply my answer for this, my output value for this will be this thing right here. So mod returns the remainder only. So that's why at the first recursive call with x is equal to 19 parameter, I am calling another recursive call with x19. At the same time, in the general case, I'm also outputting the value of 19 mod 2, which is 1. For the second recursive call with the parameter of 19 is also false. I have not achieved the base case. I will start another recursive call, but this time with 9 div2, which is 4. And also an output remainder 1, because the remainder of 9 mod 2 is 1. Following that, I have my third recursive call, this time with a parameter of 4. I still have not achieved my base case, in which case it will result in another recursive call. 4 div2 will result in 2. But since this is an even number, my mod 2 will return a 0 output. Finally, the fourth recursive call with the parameter 2, still it is false. And the outcome of this recursive call is now 2 div2, which results in the value 1. So I have a new recursive call with x is equal to x parameter 1. And at the same time, I'm returning the value of 2 mod 2, which is remainder 0. Now, I will pass 1 as my parameter. And as you can see here, my base case states that either n is equal to 0 or n is equal to 1. I have achieved the base case. So I have, in fact, achieved the base case over here. So that's why for this comparison over here, my answer is true. And since I have an answer true, I will simply output the value at that moment. So I have n as my n is 1, and I will simply output 1. And that's how my recursive call ends. Now, as you can see here, that I have a sequence of ones and zeros. In this second part of this question over here, it's asking you what is the purpose of this algorithm. So if you look closely, starting from the bottom all the way to the top, this looks like the binary sequence for the value 19. So if I look at this value from here, from bottom to top, it's something like this: 1, 0, 0, 1, 1. So if you look at the binary sequence, this is position 16, 8, 4, 2, and 1. Add them together, and we have 19. So what is the purpose of this algorithm? It turns out that this algorithm is very effectively calculating the binary version of 19, or whatever value you pass as a parameter. So it's calculating the binary version of the parameter n. That's what's happening here. Okay, so now we will look at how the stacks are used. A stack structure is used in managing the procedure of recursion. So if you come back to the procedure of factorial, if we look at this code written here, this code is implemented in such a way that I have a function definition first, And this is where my main program starts, where the function is being called. So what we understand with how programming is done, how subroutines are implemented, is that first a subroutine has to be defined. Only then it can be called in a main program. So it's not possible to call a subroutine first and define it afterwards. It has to be defined first. So my function definition starts from here, and then I can proceed to call it in my main program. So the first time that the factorial function is being called will be from my within my main program at line number 160. And let's assume that I'm passing the value 3 as in my number parameter. So every remember that this value will be copied. This is passing by value. This value will be copied to here, and I will have another procedure called with this time n is equal to 3. Sorry, n is equal to 3 as a function call. So basically, my first function call takes place at line number 160 from within my main program. My language translator, whatever it is, will follow through the definition of factorial and end up at line 30, because it's looking for factorial definition anywhere and find a function that's called factorial at line number 130. It starts execution with n is equal to 3, reaches this line, line number 180, and then here will result in my second function call, second factorial call, this time with value 2 as n minus 1. I originally was 3. Now I will pass 2, and this will result as in my second factorial call. And then again, since it's another function call, the rules of execution state that if it's a function call, my language translator will follow back to the function definition, and it will come back over here, this time with the value 2 in its parameter, follow through to this line. This result will be false because it's not yet the base case. I'll come back here, and this will result in my third function call, factorial call, this time with n2 minus 1 factorial 1 being passed as a parameter. And this will result in another time I'm finding the execution or the definition of factorial. I follow through with n is equal to 1, no base case yet. And this time I'm running the factorial with factorial 1 minus 1, which is 0. Okay, this will eventually result in my final execution, final function call with the parameter 0. Now, since I have used parameter 0, I will have achieved my base case, and this is the first time I will actually have an explicit value, and this explicit value will be carried for upward in upper layers to eventually get the final result. Now, this stack, as you can see here, this actually implements the essence of unwrapping a result. So my first function call starts from line number 160, and the parameter that I'm using, original parameter that I'm using is n is equal to 3. And now when I follow this execution over here, and I end up with the second factorial call, this time I will have used the parameter 2. So this, you see here, second call is made. Now a second call is made with n is equal to 2. So what is the result? What is the result with n is equal to 2? Yet there is no result. The result is that I have another factorial call, which is my third, this time with n is equal to 1. So that will end up over here. There's no explicit results yet. Finally, another call is made, this time with n is equal to 0. Now, since n is equal to 0 is base case, I will actually have an explicit value here, which is 1. I will use this one and implement that in the previous layer. 1 factorial of 0 multiplied by 1, 1 into 1 will result in 1. I will use this 1 and apply it to the upper layer. Factorial of 2, 2 multiplied by 1, 2. I will use this result and pass it to the upper layer or the original layer. 3 multiplied by the factorial of 2, which is 2. I will have the answer 6, which is the final answer back at line number 160. And after the whole of this procedure being executed, after all of the recursive layers, the control will be shifted back to line number 160, back to my main program, in which the variable answer will be assigned value 6. And I will, at line number 160, 170, I will output the contents of answer, and 6 will be presented on the screen. So this is how your factorial is implemented through stacks. So in the math, in math, there's a lot of is use of the Fibonacci sequence. Basically, the Fibonacci sequence states that I get the third answer, the value, the third value by adding previous two values. So for example, I get two, I add, how did I get two? I added one and one. How did I get three? I added one and two. How did I get five? I added two and three, and so on and so forth. So this is my Fibonacci sequence. Each third number is calculated by adding the previous two numbers. Now, this Fibonacci sequence can be implemented using this algorithm and is again recursively being implemented. Now, in this algorithm, Fibonacci, I'm passing a parameter n. This is my base case here. Is n equal to 0 or n is equal to 1? If n, and either one of these cases simply output 1. So as you can see here, for these two first values, n is equal to 0 and n is equal to 1, either case, I'm just outputting 1. So that's what's stated over here. So if n is equal to 0, n is equal to 1, I'm simply outputting 1. That's my result. However, if it's not the base case, if it's not the base case, then I will have, it will result in another recursive call. Recursive calls is in this way. So first I will find the Fibonacci sequence for n minus 1. I will add the result of this outcome with the Fibonacci sequence of n minus 2. And that will result in another value. And this each recursive call will eventually lead me closer to my base case, which will actually have an explicit value. So as we can see here that this is my base case, this is my general case. We are to dry run the Fibonacci algorithm with the parameter 4. Now this is what it looks like. So my first call of this function is called with the procedure, sorry, with the value 4. Have I reached the base case? No, I have not. Okay, just to keep things short, instead of writing complete Fibonacci, I just have written F here. So this does resemble, this does mean Fibonacci. It's just an abbreviation, but it is Fibonacci. So just to, I don't have a lot of space here. I just use the letter F for this. Okay. So basically, since I have not reached the base case, I will move towards the general case. And the general case means that now I will calculate the value of Fibonacci n minus 1 and Fibonacci n minus 2. So originally n was 4. So I will first calculate Fibonacci 3 and Fibonacci 2. So this will result in my second call, Fibonacci 3. Now Fibonacci 3 still is not a base case. That means I will still move towards a general case in which I'm fighting Fibonacci 2 and Fibonacci 1. Okay, moving to Fibonacci 2 now. This will be my third call. Not the base case yet either. Now I'm moving towards Fibonacci 1 and Fibonacci 0. As you can see here, that these are the two base case values, in which case Fibonacci 1 is the base case and will return the value 1. Fibonacci 0 is the base case as well, will return the value 1 again. Now, if you go back and apply these results to the upper layers, it would look something like this. Fibonacci 1 results 1, Fibonacci 0 also results 1, 1 plus 1 will result in Fibonacci 2. Now, since I have Fibonacci 2, I will use the Fibonacci 2 value, which I just gained from here, which is, by the way, 2, and add it to Fibonacci 1, which I know is 1. I will end up with Fibonacci 3. Now, since I have the Fibonacci 3 value and also know the Fibonacci 2 value from here, I'll apply the result and finally get Fibonacci 4. So as you can see here, until I have reached my base case, I will not end up with the final value. So as you can see here, Fibonacci 0 and 1 results in 1, 1. My Fibonacci 2 will result in 1 plus 1, 2. My Fibonacci 3 will result in, my Fibonacci 3 will result in 1 plus 2, 3, the value 3. And finally, my Fibonacci 4 will result in 3 plus 2, 5. So this is how my outputs are being unwrapped once I have reached my base case.